Well, hello all. I'm Stephen and I'm behind the camera today.
And this is Liz, and I'm on the side of the camera today, and you'll see my big paw um, working on some of these numbers to try to illustrate the concepts of statistics.
Right, and so just for kind of information purposes, we're going to be doing a video where Liz is going to go through with you statistics on the whiteboard. There also is, and she is sending to the class conference folder a PowerPoint which gives similar information, but this is more explanatory.
Yeah, and so I'm going to follow the PowerPoint slides in sequence, but just sort of talk us through some basic statistics. Now, some of this may be a repeat for some of you who have had statistics, and for those of you who have not studied statistics, it's an introduction to the language, the thinking processes, and the action processes of stats. Just one thing to think about as you go through this. I will often use a statistician for my research because you can't be an expert at everything. So what we can at least think about is mastering the concepts. So let's start out. The other thing I wanted to say before we begin chapter 19 and some illustrations of the kinds of statistics that we talked about in that. This chapter 18 is a short chapter that really speaks to data management, which is the ability to organize the data that you collect so that you can analyze your findings, use your data in an organized fashion to answer your research questions, and also to meet some requirements for granting agencies such as National Institutes of Health and National Science Foundation for setting up a data management plan for the protection of human subjects, as well as for the ability to share your data with other investigators. So that's basically what's covered in Chapter 18, and that's just for your information and for those of you who plan to do funded research in the future or do research, especially with large data sets. So let's start with Chapter 19. And the first part of Chapter 19 talks about descriptive statistics. And those are numbers which actually describe a distribution of scores. So if we look here, and let's say that these scores are happiness scores, where 1 is low and 10 is high. So 1 means I'm not very happy at all, and 10 means I'm elated. So if we look at the first distribution of scores, and we'll call this A, and the second distribution of scores we'll call Group B. Okay, so in Group A, our frequency would be the frequency of how many 4s, how many 5s, how many 6s, or how many 1s, 2, 3, etc., up to 10. So we have 0 frequency of 1, 0 frequency, whoop, there you go. You want to answer the phone? Sorry. No frequency of 2, etc. And then we have a frequency of a score of 4, so that 2 people answered a 4, 2 people answered 5, and 2 people answered 6. Now if we look at B, our frequency of 1 is 1 person. Our frequency of each of those scores listed here is 1. Okay, so then the percentage we would figure out, in distribution A, we have 6 scores, so 2/6 of, or 1/3, about 33% answered 4, 33% answered 5, and 33% answered 6, and so forth. And we can figure it out the same for the distribution B. Now, measures of central tendency, mean, median, and mode, are almost always the basic building blocks of statistics, in particular the mean for interval level data. We cannot use the mean or median for interval level data. For anything, for nominal data, sorry. Because let's say that here we have 2 males, and so if we have males equal 2, and females equal 4, okay? So we have, and we assign a 1 here and a 2 here. So our frequency of females would be 4, and our frequency of males would be 2. So we would get a frequency for nominal score of 1 of 2, and a frequency for a nominal score of 2 as 4, because 4 people would have checked 2 and 2 people would have checked 1. Okay, just let me get rid of those, not to muck up the rest of this stuff. So but we see that we can't add or subtract our 1s and 2s, because it really, remember, nominal scores are those that name. So male equals 1, the 1 really is not a number that can be computed, but rather a number such as your telephone number that is naming a property of you, in this case, how you can be reached on the phone. So we can compute a mode, which is the most frequently occurring score. So in the case of males and females, and where we had female is 2, the most frequently occurring score was 2. And we can then get a mode on ordinal data as well as interval data. And if you look at this, our mode here, we really don't have a most frequently occurring score. We have 3 modes, 6, 5, and 4, because each occurs twice. Here we have no modes. Okay, a median is the middle score. So here 5 is our middle score, and here 7 is our middle score. Well, actually it isn't, I'm sorry. We have an even number. So we would subtract 3 from 7 and get 4 and divide by 2. So 4 would be our median, which is the actual midpoint of the distribution of scores. Okay, the mean is the average. So, and the mean is computed on interval level data. So what we want to think about, and let's look at how this is computed, and I chose these numbers because I want to illustrate distribution. But here, let's look at, if we add these numbers together, we get 30. And we have 1, 2, 3, 4, 5, 6 scores, so we divide by 6, and we get an average or a mean of 5. And similarly here, we have a mean of 30. Of 5 rather. A total of 30 and a mean of 5. Okay? So keep that in mind, that both of these distributions have a mean of 5. So what we're going to do is say our mean score is 5. And here our mean score is also 5. So that now you might want to think about, oh, wow, well, I might think that these two groups are the same if I only look at the mean. So there's obviously something else that I have to do. I have to look at the whole distribution and look at how it is dispersed, to determine whether or not my groups are equivalent. And so what the slide number 3 talks about, and you read about in chapter 19, is that there are a number of different ways to measure dispersion or the variability of scores. So how diverse are my scores? Do they all center around or sort of cluster around a mean of 5 like the distribution in A? Or are they all over the board? So if we were going to describe in words our the happiness in group A, we would say that they're sort of not happy and not sad pretty much, and they all cluster around a mean of 5. However, if we were going to now describe the happiness in group B, we would say, oh, there are people who are very, very sad and have scored 1, and people who are very happy who have scored 9. So these are very, very different distributions. And so we can describe that in terms of range, from high to low. The sum of squares, which is you would square each one of these and then add. So you 4 times 4, 4 times 4, 5 times 5, etc. Add them together, and that would be the sum of the squares. And there's a reason for doing that. That usually, and we're not going to talk much about that, because that usually is the basis for other computations, such as computing the standard deviation. And we are going to talk about the standard deviation. Okay, so what is a standard deviation? And as you read in the chapter, the standard deviation is the average distance that each score is away from the mean. Okay, so when we think about standard deviation, what we're thinking about is, and I'm going to draw a little curve here, and then a different kind of curve here. So here we have a mean of 5, which is our average, right? And here our scores cluster around the mean. They go from 4 to 6. And here they go from 1 to 9. So if we were to figure out our standard deviation for our distribution A, it would be small. And if we would figure out our standard deviation for B, it would be large. And so as we think about standard deviation, the smaller the standard deviation, the more our scores cluster around the mean, and the more homogeneous our scores are, as in group A. They are moderately happy or unhappy, whichever, the glass is half empty or half full. And in the distribution in B, they are very dispersed, from very unhappy to very happy. Now, you might be thinking, well, so what? Well, suppose you have a distribution of scores that is similar to group A. So you know that, let's say you have 2 classes, and you're looking at their knowledge of statistics in class A. So in class A, I would assume that everybody's the same, and I probably would teach similar level of material to everybody because you had a moderate knowledge of statistics on my test. Whereas in group B, I would be much more challenged to teach to a wider range of knowledge because the statistics scores would be from very low to very high. So you see that the mean is not the only important descriptor of a distribution, but the standard deviation or other types of measures of dispersion are really, really important in looking at a group of scores and ultimately in interpreting what the scores mean. Okay, so let's get rid of this guy. And now let's talk about bivariate descriptive statistics. And by bivariate, we really are talking about 2 variables, bivariate, and they still describe. And there are a number of them, as you read in chapter 19. So I just want to illustrate the Pearson R, which again is done on interval level statistics only. Now the Pearson R goes from -1 to +1 with a 0 in between. And let's look at what the Pearson means. Let's think about height for one variable and weight for our other variable. If we have a score of 1, what that means as one variable changes a single unit, the other variable changes a single unit. So the score, a raw score of 1, an absolute value of 1, that means with no sign, really talks about a perfect correlation. As one changes a unit, the other changes a unit. So as height, and we'll use this, our y-axis for height, and our x-axis for weight. So as height goes up a unit, weight goes up a unit. Height goes up a unit, weight goes up a unit. As weight goes up a unit, height goes up a unit. And so then we draw a little line through this, and we get here a 45-degree angle line. Now, -1 is also a perfect correlation, but it is an inverse correlation. So what it means, as one goes up, in this case weight, and it doesn't matter which, because we'll see in a minute, that the other goes down a unit. As one goes up a unit, the other goes down. As one goes up, the other goes down. So, I mean, the same thing. As one goes up, the other goes down. So that it's non-directional, but just talks about what is the relationship between X and Y, height and weight, socialization skills and IQ score, socialization skills and enjoyment of the outdoors and so forth. So it doesn't really matter what the variables are, as long as they're measured intervally with interval level data, then we can compute a Pearson. Now, let's think about the Pearson. Let me just get rid of this. No relationship is a score of 0. So the closer one gets to 0, the less there's a relationship. And a score of 0 looks like a bunch of data points, height, weight, that are all over the place, that you can't even get a line through. So you can't get a line, any way. Okay? So that would be a 0. So that any score close to 0 is no relationship, and the closer the score gets to an absolute value of 1, whether it's positive or negative, the stronger the correlation. The sign on each of the values tells you whether the correlation is positive, that they both vary in the same direction, or inverse, that is, one varies one way, the other varies the other way. Okay, let me erase this guy. And a contingency table is a type of correlation also. And let's think about this. Suppose we have males and females, and let's say we have 6 here and 4 here. Okay, and we want to look at their at how tall they are. So we're going to measure them as tall or short. Okay? So what a contingency table tells us in frequencies are how many males are short, how many males are tall. So let's say that we have 2 here and 2 here, and we have 2 here and 4 here. So this tells us that we have the relation that females are shorter, in essence, in this, it doesn't tell us how much shorter, but it says that more females are short than males. How does that work?
Right.
Okay.
And for that sample.
For this sample, right, for this sample of 10. Okay. And the Spearman-Rowe and the chi-square are other statistics that also tell you about relationships and describe what is the relationship between two variables. So when we think about relationship, we're not talking about does one cause the other, but rather is one associated or related to the other. So that if we have a question such as what is the relationship between height and weight, we would answer that with a bivariate descriptive statistic. Now, suppose we want to know about cause, or we want to know other kinds of information that will answer level 3 questions. We often will go to inferential tests of group difference. Now, inferential statistics are those that infer from the sample to the population. So, if I have a finding on my sample, regardless of whether even if it's a mean score, let's say I have a mean happiness score again of 5, the question is does that represent the mean score of happiness in my population. Now, most of these inferential tests can only be done, well, legally, even though we violate that all the time, but can only be done on random samples. So we talked about the selection of sample random and non-random, and remember, random means equivalent chance, so that it eliminates, random sampling eliminates the potential for a biased sample that does not represent the population. So if we have a mean score of 5, here, the question is, to what extent does that mean score of 5 reflect the population parameter of happiness? And there are all kinds of ways that we do that. We can test by, and we look at probability, and you read a little bit about that, and I'm not going to go into that in great detail. So that there are a variety of different tests that we can use, and we get a probability which tells us within a certain degree of assuredness whether or not what we found in our sample is likely to occur in our population. Now, there are a number of different kinds of inferential tests. One looks at a single variable and its likelihood of what you find in your sample to be in your population. And then there are other types as well that will look at, for example, the difference between two groups, males and females, on happiness score. So let's say that in our last distribution, that group A was male, and we have a mean of 5, and group B was female with a mean happiness score of 5. And here, remember that we had, let's say, a very small standard deviation, so let's put it at 0.05. And here, let's say that we had a larger standard deviation, and we'll put it at 0.9. Remember, one curve looked like this, and the other curve looked like this. So now the question is, are these two groups the same? Are they equally as happy? Or is the difference in these scores, including the standard deviation as well as the mean, a difference that is caused by chance or not likely caused by chance? So that's what inferential statistics for two groups tell you. And of course we could add a third group, and perhaps there we would add, let's say, bisexual kids, and maybe we would have a different, let's say we have a similar mean and even a larger standard deviation. So we get even a flatter curve of, let's say, 1.3. And so now the question that we would want to ask ourselves, are bisexual kids and females and males equivalent or not? And if we find differences in the distribution of their happiness scores, are these chance occurrences or are they not? And that's what all inferential statistics tell us. And the way in which they are computed really requires us to infer from our sample to our population, which is one of the limitations of those statistics for a lot of the questions that we often ask in social science research, in educational research, and so forth. But we use them anyway, and we use them with limitations, even if we don't have a random sample. Okay, that's it for my drawing, so let's get rid of you. And I just wanted to tell you a couple of other things about associational statistics there that you saw in chapter 19. Multiple regressions are used to tell you out of a number of factors what predicts an outcome. And so are discriminant function analyses. So let's say that you have 5 different variables. You have socioeconomic status, diagnosis, height, weight, and socialization, maturity. And you want to predict whether or not a kid is going to do well in a certain situation. So the outcome variable might be how well will that kid thrive in a classroom. So you have a lot of different variables that are predictor variables that you want to use to predict a certain outcome. So for those, we can use both multiple regression and discriminant function analyses, depending on what level of data is used to measure the outcome variable or the dependent variable. And finally, one of the things that I wanted to conclude with is that there are also a number of different techniques that as computers become more omnipotent and more complex, that we use in statistical analysis, geostatistical analysis being one of them, which allows us to locate data in a geographic area. So Stephen did some research on looking at the concentration of substance abuse prevention services in particular areas in Maine. And he used geostatistical mapping to look at not only how many services and what was the concentration, but where were they located. And then related that to patterns of substance abuse to see if there was any relationship between the presence of prevention services and the magnitude of substance abuse. There are other forms of visual analysis as well. Many of them are used in single case studies, etc. And you read about those, and I'm not going to go over those, in great detail. But just be aware that they're increasingly used, visual analyses in the form of maps, in the form of graphs, in the form of different lines, etc. all tell us a story about our data.
Well, and one of the things, Liz, we should probably say, and I know that they don't have any reading to do for this particular course, but kind of thinking of
I think that was a joke.
that was a joke. But thinking about these other forms of visual analysis, we should probably send them the reference for, was it Tuft?
Edward Tooft.
Edward Tooft, because
Tooft.
Tooft does really a wonderful job of laying out and showing how the visual analysis can really enhance your presentation of data, and it can be done in both an attractive way, but also a way that really enhances the story that you're wanting to tell.
Yeah, he talks about visual data as elegant, and
Right.
so he really has. He's a thoughtful and very creative guy who really has made artwork out of statistics.
Right, so we should send them that
Yeah.
reference, and that would be something.
Okay, and the
take a
other
look
thing
at.
that we're going to do is we're going to do a narrated PowerPoint on the other reading that you have, which is the ICF.
Oh.
So stay tuned for that one.
Yes, one of my favorite ones. Okay,
Bye-bye.
bye-bye now.